Hey everyone, and welcome back to What Is Day. We're tackling a topic that's as powerful as it is misunderstood. A source of energy that conjures images of both futuristic utopias and glow-in-the-dark dangers. We're diving deep into the heart of the matter to ask, what is nuclear energy? Is it a clean energy savior or a ticking time bomb? Let's crack open the atom and find out. Don't worry, we'll keep it safe, contained, and hopefully a little enlightening. Metaphorically speaking, of course. To understand nuclear energy, we have to start at the very, very beginning. No, not the Big Bang, tempting as that is. We need to go smaller. Much, much smaller, to the atom. Everything around you, including you, is made of these tiny building blocks. And at the heart of every atom is its nucleus, a tightly packed bundle of protons and neutrons. Now, these particles in the nucleus are held together by an incredibly strong force, often called the strong nuclear force. Think of it like the universe's most stubborn superglue. It's so powerful that if you manage to mess with it, you can release an extraordinary amount of energy. And that, my friends, is the foundational secret of nuclear power. It's like finding a treasure chest, but the treasure is raw power, and the chest is smaller than a speck of dust. The trick to unlocking this power isn't about making atoms bigger, but about making them smaller. Or, more accurately, splitting them. This process is called nuclear fission. Imagine trying to split a tiny, incredibly dense peach pit. You need a targeted impact. In nuclear fission, our peach pit is usually an atom of uranium-235, a specific, heavy isotope of uranium. And our impact tool, a neutron, a tiny, uncharged particle, acting like the universe's smallest, most precise bowling ball. When a neutron hits a uranium-235 nucleus just right, that nucleus becomes unstable and splits into two or more smaller nuclei. But here's the magic trick. When it splits, it also releases more neutrons and a whole lot of energy. This energy, by the way, is a direct consequence of Einstein's famous E=mc² equation. A tiny bit of mass is converted into a huge amount of energy. It's literally turning matter into pure power. Now, those newly released neutrons from the first split, they go on to hit other uranium-235 atoms, causing them to split, releasing more neutrons, and so on. This is what we call a chain reaction. It's like dominoes, but instead of falling, each domino explodes and sets off 3 more exploding dominoes. If left uncontrolled, you get a very rapid, very energetic event, which is great for, say, a bomb, but not so much for keeping the lights on. So, how do we harness this controlled explosion to power our homes? Well, that's where the nuclear power plant comes in. Its job is to manage that chain reaction, slow it down, and turn the released energy into usable electricity. Inside the heart of a nuclear power plant is the reactor core. This is where the uranium fuel, usually in the form of ceramic pellets, is housed in long rods. These fuel rods are carefully arranged, and positioned amongst them are control rods made of materials like boron or cadmium. These control rods are like the brakes for our atomic bowling alley. They absorb excess neutrons, preventing the chain reaction from getting out of hand. By raising or lowering them, operators can precisely control the rate of fission, and thus, the amount of heat generated. And what happens with all that heat? It boils water. Simple as that. The fission process heats water, turning it into high-pressure steam. This isn't just any steam, it's like supercharged steam, eager to do some work. The steam then travels to a turbine, which is essentially a giant fan. The high-pressure steam pushes against the blades of the turbine, causing it to spin at incredible speeds. This spinning turbine is connected to a generator. And a generator, in its simplest form, uses magnets and coils of wire to convert mechanical energy, the spinning, into electrical energy. Bam! Electricity delivered to your home. Finally, after driving the turbine, the steam needs to be cooled back into water so it can be reused. This is where those iconic, often misunderstood, cooling towers come in. A common misconception is that these towering structures are spewing out smoke or dangerous pollutants. In reality, they're mostly just releasing water vapor, essentially, big clouds as they dissipate excess heat into the atmosphere. The cycle then repeats, round and round, generating power for years. So, that's the how. Now, let's talk about the why and why not. Nuclear energy has some compelling advantages. First and foremost, it's a major source of carbon-free electricity. Unlike burning fossil fuels, nuclear power plants don't release greenhouse gases, like carbon dioxide, during operation. This makes it a crucial tool in the fight against climate change. It's also incredibly reliable. Unlike solar or wind, which depend on sunshine or breezes, nuclear power can operate 24/7, providing what's known as baseload power, a constant, steady supply of electricity that grids desperately need. And it requires very little fuel for a lot of energy. A single uranium pellet, smaller than your fingertip, can contain as much energy as a ton of coal. Imagine trying to barbecue with that. However, nuclear energy isn't without its challenges, and these are often the points of public concern. The first is radioactive waste. When uranium atoms split, they create byproducts that are radioactive and remain so for thousands of years. Safely storing this waste is a serious, long-term challenge that society is still working to fully resolve. It's not just glowing green goo you can leave in your backyard. It requires highly specialized, secure containment. Then there are safety concerns, often brought to the forefront by incidents like Chernobyl or Fukushima. These events, though rare, highlight the catastrophic potential when things go wrong. Modern nuclear power plants are built with multiple layers of safety systems and containment. Learning from past mistakes, the industry is probably one of the most heavily regulated in the world, precisely because of the stakes involved. No, Homer Simpson isn't usually in charge of control rods, thankfully, but despite these challenges, the future of nuclear energy is evolving. We're seeing advancements like small modular reactors, or SMRs. These are smaller, simpler, and potentially safer reactors that can be built in factories, improving construction efficiency and potentially reducing costs. They offer greater flexibility for grid integration and can be deployed more quickly than traditional large-scale plants. There's also the tantalizing prospect of nuclear fusion, which is the opposite of fission. Instead of splitting atoms, fusion involves combining them, the same process that powers our sun. If we can ever harness controlled fusion here on Earth, it would offer virtually limitless, clean energy with minimal radioactive waste. But that's still a few decades, or perhaps even a few centuries, away from commercial viability. For now, fission is the workhorse. So, what have we learned? Nuclear energy is a powerful, complex technology that harnesses the fundamental forces within atoms. It offers a reliable low-carbon source of electricity, but comes with significant challenges related to waste management and safety. It's a tool, like any other, that demands careful handling, continuous innovation, and a thorough understanding of its immense potential and its inherent risks. What do you think about nuclear energy? Is it an essential part of our energy future, or are the risks too great? Let us know your thoughts in the comments below. If you found this video illuminating, give us a thumbs up. Subscribe to What Is for more deep dives into complex topics, and hit that notification bell so you don't miss our next video. We love exploring the world's mysteries with you. Stay curious.